This is the American space probe, Voyager. It's on its way through the outer planets of our solar system. When we were recording this program, it was just approaching Saturn, and the idea is for it to take measurements of Saturn. But how does Voyager know where Saturn is? How does a spacecraft know which way to point its instruments? Well, Voyager is controlled from Earth, and we on Earth know where Saturn is at any moment of time. We can set up a system of three-dimensional axes and then find the coordinates of the center of Saturn relative to these axes. So from Earth, we can find for Saturn a triple of coordinates x, y, and z. These numbers could be very large. If we were working to Mars, there would be hundreds of millions. But nevertheless, we could find the coordinates. Now, on Earth, we also know where Voyager is. It's got coordinates relative to Earth. But where's Saturn relative to Voyager? Well, Voyager has got its own system of axes. It's determined by gyroscopes and star positions. What we've got to find are the coordinates of Saturn, x dashed, y dashed, z dashed, relative to this set of axes. Now, the answer looks incredibly complicated. It's got sines and cosines of angles alpha, beta, and gamma, and other numbers, a's, b's, and c's. And there doesn't seem to be much of a pattern to it either. But in this program, we'll see that by using matrices, not only will we establish this result quite easily, but we'll also see that there's a simple structure to these equations and the way they're made up. We'll take it in two stages. First, we'll look at the general strategy, and then we'll look into the mathematics to implement that strategy. Basically, it's a problem of change of axes in three dimensions. We've got a set of axes where the Earth is, and a point, Saturn, with coordinates relative to these axes. But we want to change the axes. We want to move the origin, and then we want to change the direction of the axes. This change of axes can be done in two stages. First, we get the origin in the right place without changing the direction of the axes. This is just a translation. It's a straightforward problem in vector addition. Secondly, once we've got the origin in the right place, we have to reorientate the axes so that they're aligned correctly. We'll look at the two stages of this change of axes separately, and we'll deal first with the translation. We've got a three-dimensional system of axes and a point whose coordinates are x, y, z relative to this set of axes. But what we want to do is to move the origin to a point A, B, C. And what are the coordinates of this point relative to the new set of axes? We want to find this vector, but there are two vectors that we know. We know the position vector of the point relative to Earth, and we know the position vector of the new origin relative to Earth. So the vector that we want is just s minus v. The coordinates of s are just x, y, z, and v is the position of the new origin, so its coordinates are just a, b, c. So the coordinates of the point relative to the new set of axes are just x minus a, y minus b, and z minus c. That's the result of the translation. But we're trying to get from x, y, z to the new coordinates x dashed, y dashed, and z dashed. We've just done the translation. That's given us coordinates u, v, w, which are simply x, y, z minus a, b, c. We now want to reorientate the axes. From the coordinates u, v, w, we want to find the coordinates x dashed, y dashed, and z dashed. Now this is the second stage of our problem. The translation's got the origin in the right place. What we've got to do now is to get the axes pointing in the right direction. On this model, the axes are freely pivoted. And what I'm looking for is a systematic procedure for reorientating the axes. Now, there's no simple single instruction that will reorientate them in one go, but supposing, to start with, we had a simpler problem. Supposing we had the z-axes aligned like that. Now, can you see that these four axes now all lie in a single plane? And because they lie in a single plane, what we can do is to rotate about this z-axis. We can rotate like that and get the x and y axes aligned. And that's the clue to what we want to do. What we're going to do is to use a sequence of rotations, each one of which keeps one of the axes fixed. Now, there are all sorts of different procedures that you could adopt, but the most usual one goes like this. What I'm going to do is to rotate first about this z-axis, and I'm going to rotate just enough to get these three axes in a single plane. And once they're in a single plane, I can now rotate about the x-axis here just sufficiently to get the z-axes aligned. Now, of course, this is the problem we've just seen. It's the simpler problem. These four are in a plane. I can rotate about the z-axis just like that to finish the job. So there are three steps in the reorientation. First, we keep the z-axis fixed and rotate about the z-axis. Second, we keep the x-axis fixed and rotate about the x-axis. Thirdly, we finish the job with a rotation about the z-axis. Now, when we do a rotation, we record that by measuring an angle. So the first rotation will be a rotation through some angle alpha. The second rotation will be through some angle beta. And finally, a rotation through gamma will finish the reorientation. This is a standard procedure for performing any three-dimensional reorientation. When you know the values for alpha, beta, and gamma, then the reorientation is completely defined. So Voyager, by using its gyroscopes and looking at fixed star positions, keeps track of its orientation simply by storing information about these three angles. So let's look back over our problem. What we've got is a problem of change of axes in 3 dimensions. And we do it in 2 stages. First, a translation, and we follow that by a rotation. The mathematics of the translation is just vector subtraction. But the reorientation is far more tricky. But we've now got a strategy for doing the reorientation. We do it by 3 rotations. But how do we express these rotations mathematically? And how do we express mathematically the combination of rotations to form the complete reorientation?
What Norman has done is to break the reorientation down to 3 simpler rotations, each of which leaves one axis fixed. We'll look at what happens to the coordinates of a point in 3 dimensions after applying a rotation about a fixed axis. Now, here's a system of 3 axes and a point with coordinates u, v, and w relative to these axes. Now, I can rotate these axes about the z-axis. What will the coordinates be after I've changed these axes? Well, let the new coordinates be u dashed, v dashed, and w dashed. We want to find expressions for u dashed, v dashed, and w dashed in terms of u, v, and w, and this angle alpha. Let's look at the z-coordinate first. That's this length, w. What happens to this coordinate when I rotate the axes? Nothing. The z-coordinate is completely unaffected by this rotation. So, w dashed is simply equal to w. What about the x and y coordinates? We'll look at the effect of the rotation from above. From here, you can't see the z-axis, and the rotation just looks like a 2-dimensional rotation of the x and y axes. And we've met this before. So, let's look at the 2-dimensional problem. We'll look at a point, uv, in the xy plane. What happens when we rotate these axes through an angle alpha? What are the coordinates of this point relative to these new axes? Now, the new x-coordinate is just this length, and the new y-coordinate is just this length. And these lengths we can find geometrically. Consider the point in the xy plane with coordinates u, v. But we want to change these axes. What are the coordinates of the point with respect to these rotated axes? We need to find two lengths. The first coordinate is just the length along the new x-axis. We'll find this length in two parts. The first part comes from this right-angled triangle. Since the hypotenuse is of length u, the length we want is u cos alpha. What about the other length? To find this, we need to look at another right-angled triangle. It's just the length of this side. The hypotenuse is v, and this angle is alpha. So the length we want is v sine alpha. So the new x-coordinate is u cos alpha plus v sine alpha. That's the new x-coordinate. The new y-coordinate uses the same triangles. This time we want the difference of two lengths. This length is v cos alpha, and this length is u sine alpha. So the new y-coordinate is v cos alpha minus u sine alpha. So now we have three equations which tell us the coordinates of the point relative to the new set of axes in terms of the original coordinates and the angle alpha. But these are three equations, and they involve u, v, w, and the angle alpha, all mixed together. There's a simpler and more informative way of writing these equations, and the way to do it is to use matrices.
Well, Mix just found three equations that express the coordinates of a point after a rotation about the z-axis in terms of the original coordinates. So we have an equation for u dashed, the new x-coordinate, in terms of u, v, and the angle alpha we rotated through. Another equation for v in terms of u, v, and alpha. And the z-coordinate, well, that doesn't change. We simply get w dashed equals w. Well, rewriting these equations in matrix form will help us solve the more complex reorientation problem we had in the beginning. So how do we express these as matrices? Well, these expressions look very similar to linear simultaneous equations, and equations of this form can be written as a matrix times a column vector. The column vector, well, that's just u, v, w, the old coordinates. And the matrix, well, that's just formed from the coefficients of these equations. So for the first line, you get cos alpha, sine alpha, and no w's, 0. Cos alpha, sine alpha, 0. Second line of the matrix, you get minus sine alpha, cos alpha, and again no w's, 0. And the third line, no u's, no v's, just one w. Checking this matrix product really does give us these equations. We'll check the first equation. So we get u dashed. Doing the matrix multiplication, we get u cos alpha plus v sine alpha and no w's. That's our first equation, and so on. This is the matrix form of these equations. It expresses the new coordinates as a column vector in terms of a square matrix times the column vector of our old coordinates. Well, there's another way of looking at this matrix equation. You can think of this matrix as representing an operation, the operation of rotating through an angle alpha about the z-axis. And it operates on the coordinates u, v, w to give us the new coordinates u dash, v dash, w dash. So, to perform the operation of rotating the axis through an angle alpha about the z-axis, you simply multiply the coordinates by this matrix. So matrix multiplication gives us a convenient way of describing a rotation about a fixed axis. In the more complex reorientation problem, this is going to be particularly useful because we have 3 rotations to do, one after the other.
So let's just recap where the rotations came from. First, we rotated about the z-axis through an angle alpha, then through an angle beta about the x-axis, and again about the z-axis, this time through an angle gamma. So what we've got is a combination of 3 rotations for the reorientation. We rotate through an angle alpha about the z-axis, then through an angle beta about the x-axis, and finally another rotation about the z-axis, this time through an angle gamma. Now, Jen's already shown us how to find a matrix which represents this rotation about the z-axis. And of course we'd get a similar matrix for the final rotation because that also is about the z-axis. The only problem that remains is how to find this rotation through an angle beta about the x-axis. What does the matrix look like for a rotation that keeps the x-axis fixed?
Our second rotation also leaves one of the coordinate axes fixed, so I can use this model again, thinking about it in a slightly different way. This time it's the x-axis which remains fixed, so it's just a rotation of the y and z axes. Now this point has coordinates u dash, v dash and w dash with respect to these axes. But what are the coordinates if I rotate these axes through an angle beta? Look at the x-coordinate first. That's this length. Well, this length doesn't change under the rotation. So the new x-coordinate, u double dashed, is just u dashed. It's not affected by the rotation. Well, what about the v double dashed and w double dashed, the y and z coordinates? Well, look at what happens in the yz plane. We have a rotation of the y and z axes. And we know the effect of a rotation of axes on the coordinates of a point. We did that earlier in the program. The new y-coordinate, v double dashed, is equal to v dash cos beta plus w dash sine beta, and the new z-coordinate, w double dashed, is minus v dash sine beta plus w dash cos beta. Now these are 3 equations. They give us the new coordinates with respect to the old coordinates and the angle beta. Now, we can write these equations in matrix form. It's similar to the matrix we saw earlier. But this time, the x-axis is fixed, so the new x-coordinate, u double dashed, is just 1 times u dashed. And this block represents the rotation of the y and z axes. Once again, we have a matrix that only depends on the angle of rotation. This matrix operates on the old coordinates to give the new coordinates. So the rotation about the x-axis through an angle beta is performed by multiplying by this matrix. That's our second rotation. The third rotation is another rotation about the z-axis. And we've already found the matrix for a rotation about the z-axis. So now we want to put them all together to perform the whole reorientation.
And here are the 3 matrices. So to carry out the whole reorientation process, we start with a rotation about an angle alpha about the z-axis. And we do this by multiplying with this matrix. This matrix is in terms of alpha, and we'll call it M alpha. Then we rotate through an angle beta about the x-axis. Well, Mick's just found we do that by multiplying by this matrix. This matrix is expressed entirely in terms of beta, and we'll call that M beta. The final step is to rotate through gamma about the z-axis. Well, this is the same as the first rotation, except we rotate through gamma instead of alpha. So the matrix we multiply by is the same as the first one, except with gamma instead of alpha. We'll call this matrix M gamma. But to do the whole reorientation process, we must do these rotations one after the other. So we must multiply by these matrices, one after the other. First we multiply by M alpha, then we multiply by M beta, and then finally by M gamma. So we start with a column vector of the coordinates. Our first operation is the rotation alpha. We multiply this vector by M alpha. This product is another column vector. It gives the new coordinates after the first rotation. We now want to change those coordinates again. We want to rotate by beta. We do this by multiplying by M beta. Finally, we want to find the coordinates after a rotation gamma. We want to multiply by M gamma. But there's another way to write this expression, which uses the fact that matrix multiplication is associative. So we can multiply these matrices together before we operate on the coordinates. So the reorientation is performed by these three matrices operating on our original coordinates. And these matrices can be multiplied together to give us a single matrix. The matrices M alpha, M beta, and M gamma are all quite simple, so their product isn't difficult to work out. And this single matrix operating on the coordinates u, v, w can then be used to perform the entire reorientation of the axes.
So that's the reorientation. It can be performed by multiplying by one 3 by 3 matrix. But before we applied the reorientation, we'd done a translation of the axes. And the translation was just a vector subtraction. So doing the translation first, followed by the reorientation, we get a matrix equation which completely describes the entire change of axes problem. This matrix equation is a lot easier to write than the 3 long equations we had at the start of the program. But really, it's exactly the same. If you multiply out these matrices to get the 3 equations they represent, you'll get the 3 equations we showed you right at the beginning. So by using matrices, we've established how to calculate the coordinates of Saturn relative to Voyager. And on the way, we've seen 2 of the major advantages of using matrices. First, it makes the equations a lot easier to write down. And secondly, in this matrix equation, we can actually see the structure of how the equations were formed. First the translation, and then the 3 rotations.